Okay, let's get started. Everyone, good morning. Topics for today, we're going to wrap up the IP header. We had two little topics left to cover there and start on reliability. This is the topic for your second project. So we're going to get started on that today and then continue it after the midterm. So on the question of designing IP, two topics that were remaining. One was we wanted to take a brief peek at IPv6, really through the lens of what's changed, what's different going from IPv4 to IPv6. And then spend a little bit of time again talking about the security implications of the IP header. And so jumping straight into IPv6, I think Murphy touched on this a little bit in his lecture on addressing, but just to recap, roughly about the late 90s, people started panicking that with 32-bit IPv4 addresses, we're going to run out of address space fairly quickly. And so IPv6 was an effort that started, it was motivated by this concern about address exhaustion. And so IPv6 goes all the way to the other extreme. Addresses are 128 bits long, so they have 4 times more bits than in IPv4. So it seems very likely at this point that we're never going to run out of addresses using IPv6. Where is IPv6? It has been a slow process of deployment. At this point in time, I would say, I think depending on which numbers you believe, between 30 to 40% of the internet is using IPv6. But, there have been major announcements. For example, all of China has said that they're moving to IPv6. All of the major cloud providers support IPv6. So at this point in time, there's no question that IPv6 will one day be the version of IP running on the internet. It's just a question of how much time it's going to take to get deployed. While IPv6 was primarily motivated by this concern about we need more address space, we've run out of addresses to allocate, the designers of IPv6 also took the opportunity to do a little bit of a cleanup on the IPv4 header. So we've talked as we went through the IPv4 header about why do we have this field. This field looks complicated. Operators don't really turn on this other field and so on. So they did a little bit of, let's call it spring cleaning on the IPv4 header when going from IPv4 to IPv6. That's about the extent to which the designers tried to effect change, going from v4 to v6. So, for example, some of the things they did not touch or did not address were things like security and concerns about IP address integrity and so on, which we'll touch on. So overall, I would say IPv6 is nicely designed. It's an elegant protocol, and the changes they made make sense and are nicely done. It's not a particularly ambitious protocol. So everything we've learned about IPv4 still applies to IPv6 with a few changes to the IP header that we'll talk about. Okay. So with that, here's the IPv4 header. We talked about it last time. If you need a reminder, there are a few fields up there, versions, header lengths, and so on, that were for parsing. There's a source and destination address, of course. Then there are a few fields to deal with issues like fragmentation, looping, checksums if packets get corrupted. And then there were a few fields in there to deal with what if you wanted exception processing, so type of service or this notion of options, where you can ask for advanced functionality. So if you were doing IPv6, what cleanup would you do? We're going to increase the size of the addresses, so let's take that as a given. But what else would you clean up, change, do differently? Yeah. Remove the checksum. Anything else that can go? Or that you don't like, you would do differently? You don't have to know how to fix it, just things that didn't please you about the v4 header. Okay, we'll take the checksum. Let's start with that. So summary of changes, we expanded addresses. We eliminated the checksum. Why did we eliminate the checksum? Because as we discussed in class, you could have just let a corrupted packet go all the way to the receiver and have the receiver check whether the checksum was correct. And if it wasn't, it could drop it. Right. So strictly speaking, we didn't have to have every router recomputing and checking the checksum. The only thing you wasted by having the corrupted packet go all the way to the receiver was a little bit of extra bandwidth along the path. Okay. So that's why we eliminated the checksum. I'm going to tell you that IPv6, for fairly similar reasoning, eliminated fragmentation. You've now done fragmentation in section. So how would you deal with a packet that is larger than the MTU if you didn't have fragmentation support at routers? The end host could, which end host? You're on the right track. The sender. How would the sender know that it has to fragment? Yeah? Yeah, so that's exactly what IPv6 does. So in IPv6, the way this works is if the sender sends a packet that is larger than the link MTU, that packet is going to make its way through the network until it reaches the link where the MTU is smaller than the packet size. That router is going to drop the packet and send an error message back to the sender saying, you need to send smaller packets, this is my MTU. And then the sender is going to actually send out packets that are the correct size. So again, trying to push work off to the end host. Did that make sense to everyone? The other thing that IPv6 changes is the options, how options are handled. So if you remember when we talked about options, we said, well, because you have options, the header length is variable, which means you typically have more complicated processing at the router. Rob was saying how typically at Google, for example, they don't even treat options. They ignore them or they drop packets that have options. So options in general have been a little bit of a troublesome thing in the IPv4 header. And so the way IPv6 addresses this is it kind of says options are not part of the IPv6 header, but it gives you a mechanism by which you can still have options somewhere else. And the way it does that is actually pretty clever. If you remember going back to the IPv4 header, we had this protocol field, which we said we are going to use to tell the end host what is the layer 4 protocol you're going to have. And we said they're well-known protocol numbers. So for example, if you said my protocol field is 6, that was telling the receiver that your next header is a TCP header. Okay? So in IPv6, this protocol field is now called a next header field. And it still does the original job. So if your next header field says 6, that tells the receiver that your next header is TCP. But in addition, what IPv6 says is that you could, if you wanted to have options, so let's say, for example, you wanted to do source routing as an option, then the way you do that is you go define a source routing header. You go to the standards body and you say, I need an option for source routing. This is what my source routing header is going to look like. And you get the equivalent of a protocol number that tells the router that your next header is a source routing header. And so now if you want to have options, the only thing you have to do in the IPv6 header is that you say that your next header field is a source routing header. And then when the router can go look at the source routing header, and in the source routing header, the next header field would tell you that the header inside one level is TCP. And you could continue to do that. You can start to chain these options. So you could have an IPv6 header that's pointing to something like a source routing header. The source routing header, this is another type of header, could be an authentication header where you're checking that this is a valid packet. And ultimately, talking to the next header would be a TCP header. Okay? So the way to think about it is options have gone from the IPv6 header. The IPv6 header doesn't need to know about options. But there's this way of squeezing them in between the IPv6 header and the layer 4, the TCP header. Okay? Any questions on that? Yep.
So wouldn't the fragmentation mechanism slow down the entire network if you keep on having to set it over and over again until it's the right size?
So going back to the fragmentation question, great question. What if I had an MTU on let's say the source was initially sending 1,000 byte packets, and there's an MTU, a link that has an MTU of say 500 bytes, and then after that there's a link that has an MTU of 250 bytes. So you're right, in that case what would happen is you would send a 1,000 byte packet, you would get back an error message saying you have to send something less than 500. If you then send 499, it's going to go to the next link, which will send you another error message. So yes, you're right, that could happen, and it would happen once along the path, until the source learns it. The reason no one's too worried about that is at this point everyone is kind of settled. It's not official, but everyone kind of agrees that the Ethernet MTU is the MTU of the internet, so 1,500 bytes. So you'd have to be doing something pretty unusual to do that.